Hello everybody, this is Unit 1, Atomic Structure, Section 2, Isotopes, Decay, and Average Atomic Mass. So I really like this section of notes because it talks about radioactivity, and I'm really excited to talk about that with you guys. We're going to do an awesome project, and I think you'll have a lot of fun with it. So in front of you, you should have your guided notes. Make sure that if there's ever any point in time where you are staring at those guided notes and you've rewound the videos a couple times and you still don't know what I'm saying, even after you've rewatched it, make sure you highlight that section so that you can come talk to me about it during Access or ask a question during class. So your last video talks about the difference between atoms and ions, and we talked a little bit about isotopes, but not too much. So an isotope really happens when we have atoms of the same element that have different masses. And this really happens when an atom loses or gains neutrons. Because remember, if we change the number of protons, that changes the element. So we're not talking about protons changing. Right now we're just talking about the neutrons changing. And generally this happens during nuclear decay, which is radioactivity. We'll talk about that a little bit later. So this affects the mass of the atom, specifically the mass number, but since neutrons don't have any charge, it doesn't change the charge of the atom at all. If you look at the picture on the right, we've got a carbon-12 atom right here on the left side of this picture. Okay, so we got our carbon-12 atom there. All carbon atoms have 6 protons, and in that case it also has 6 neutrons, with the 12 representing protons plus neutrons. Remember, that is the mass number. The carbon-14 on the right side is still carbon with 6 protons, but since that carbon has a mass number of 14, we need to figure out how many neutrons that is. 14 minus 6 gives us 8. So carbon-12 has 6 neutrons, while carbon-14 has 8 neutrons. And really the only difference is the mass number, and the number of neutrons. So since they're both carbons, and we've shown that we can have carbons of different masses, carbon-12, carbon-14, there's also a carbon-13, we need to show kind of what the average is. What do most carbon atoms have a mass of? And we use that is the actual number on the periodic table. That's what your average atomic mass represents. And it's really important that you say all 3 of those words there. Because atomic mass, if you say that, I don't know if you mean mass number, which is for an individual atom, or if you're talking about all atoms of that type of element. So we really refer to mass either as mass number, when we're talking about one singular atom, protons plus neutrons, or we refer to the atoms of that element as a whole, as in all carbon atoms, and then we would refer to the mass as being the average atomic mass. And that's because we need to take into account the masses of all those isotopes, the weighted average mass of all the naturally occurring isotopes of that element. So that means that we need to factor in something called the percent abundance of that particular isotope. We're going to talk about the fact that most of the carbon atoms in the world are carbon-12. There's only a teeny tiny amount that are carbon-14. So that means that our average has to be closer to 12 because there's more carbon-12 atoms out there. So we're going to figure out how to do the math to figure out exactly how do we do an average but make the average weighted towards the more abundant isotope. So you've seen this picture before. This is an isotope or 2 isotopes of lithium. So we've got lithium-7 and lithium-6. Remember, the 7 and the 6 are representing our mass number. Mass number is equal to protons plus neutrons. All lithium atoms have 3 protons, and we can see that up here, 3 protons. They both have 3 protons. But lithium-7 has 4 neutrons. 4 plus 3 equals 7. That's the mass number. And over here, lithium-6 has 3 neutrons. That's why it has a mass number of 6. So if you're given the mass number for an individual atom, you can solve for the number of neutrons. So before we even move on, I want you to go down to the first question in your practice problems and go ahead and answer question number 1 in your practice problems. So now we know what isotopes are, but we don't really know why they matter yet. And it all has to do with this thing called radioactive decay. And this happens when isotopes are unstable. So remember, isotopes, when we're talking about that, we're really talking about what's going on in the nucleus. And really, the rule is that if we have too many or too few neutrons, then the nucleus becomes unstable. There's not a specific number for what is too many or too few, but there's a balance there. And if the nucleus becomes unstable, then it starts trying to become stable. And the way it does that is by emitting or kicking out particles or energy in order to reach a more stable state. There's a lot of ways this can happen. We're going to focus on 4. Now, I don't want you to memorize all of these. What I do want you to know is I want you to be able to match up these equation symbols with the type of decay. So I would go through and I would make some flashcards for that if I were you, because you will need to be able to identify those each on a test and kind of be able to match them up. So let's do a quick walkthrough of each of them. So the first one is alpha decay. So in order to understand alpha decay, you need to really know what happens, how neutrons were formed at the start of the universe. So at the start of the universe, we had electrons, and then electrons kind of glommed together to form protons, and then protons and electrons glommed together to form neutrons. This is like the very beginning of the universe. So essentially what I'm telling you is that in order for a proton to for a neutron to exist, we combined an electron and a proton together, a negative charge and a positive charge, to make something that was neutral. Okay, this is going to be an important concept. So when we have the negative part and a positive part of a neutron, that means that there are things that are smaller than neutrons that made up what the neutron is. That's going to be important. So during alpha decay, what happens when the nucleus is unstable during alpha decay, it wants to kick out what we call an alpha particle. That's this guy here. So it's a helium nucleus with an atomic number of 2, so 2 protons, and a mass number of 4. So that's 2 neutrons and 2 protons there. So during alpha decay, the atom emits 2 neutrons and 2 protons, and that causes the atomic number to change by 2 and the atomic mass to go down by 4. So what we're going to be doing with this is we're just going to be balancing some equations here. You'll see on the next slide what that looks like. So with beta negative decay, there's 2 beta decays. With beta negative decay, a neutron releases a negative particle and turns it into a proton. So remember I said that neutrons are made out of essentially protons and electrons. So if the neutron kicks out an electron, then what is left is a proton. Okay, so this guy left, he's gone, and we're left with this proton. So now we have a positively charged thing. So let me get rid of all this. Get rid of all that. Nope, not all that. Okay, we're back. So the neutron releases a negative particle, turning it into a proton. That's going to cause the atomic number to go up by 1 because we now have 1 more proton. But since all we did was release an electron, we got rid of something that was negative, and the negative thing has no mass. That electron has no mass, so nothing happens to the mass number there. For beta positive decay, a proton releases a positive particle, and this positive particle is technically called a positron. You do not need to memorize the name of that. But a proton will release a positive particle, turning it into a neutron. So think about that. We've got a proton, and the proton is +1 charge. And if the proton releases a positron, which is also positive, then what's going to be left is just something that is neutral with 0 charge. So what's neutral with the 0 charge? A neutron. So we release a positron, which is this guy over here, and since we kicked out a positively charged thing, our atomic number is going to go down by 1, but since we're essentially talking about a positive electron here, it has no mass, so the mass number doesn't change at all. The last one is gamma decay, and this is the one that we always talk about when we're talking about radiation, when we're talking about like Chernobyl. We're talking about gamma radiation, gamma decay. So this is really just energy. It's not a particle, it's just energy. We'll be getting into what kind of energy this is a little bit later, but because it is just energy, there is no change in mass, there's no change in atomic number, it's just a butt ton of energy that is released, and as we know from Chernobyl, it can really hurt you. Alright, so here's the types of problems we would give you. So I would, if I were going to give this to you, I would cover up this part. Okay, and I would tell you that I have uranium-235 and it decays into thorium-231. And you would have to go, what happened here? Okay, well, we have our mass number, and I'm going to look at this mass number and see what happened. Okay, we had 235 and we have 231. So the mass number went down by 4. Okay, so something happened with 4. And then we have the atomic number, which went down by 2. So what particle do we know that has a 4 for the mass and a 2 for the atomic number? Oh, well that's easy. That was our helium particle here. So I'm not going to ask you guys to make this all from scratch. My goodness, why is things not erasing? But what I would ask you to do is to be able to identify what type of decay it is or to match this particle here. And all you're doing is adding and subtracting, okay? So I'll do that one more time. We have 2 plus 90 gives us 92. 4 plus 231 gives us 235. That's all you needed to do. So the last slide looked scary, but it's really pretty easy once you get into the actual work here. Okay, so again for this one, let's cover up what we know about beta decay. So let's pretend that this wasn't here and we had to make this up on our own. So I have 92 and I have 93. Okay, so we ended up, we need to have 92 on this side. Okay, the only way I can get to 92 is by having a -1 on bottom. And then up top we have 235 and 235. So nothing happened to the top number. So we need something with 0, -1. That is going to be our beta negative particle. Okay, the last one is our gamma decay. And let's pretend we didn't know the gamma particle was there. I've got 235 here, 235 there. Nothing happened to the mass number, so it has to have a 0 on top. 92 here, 92 here, so nothing happened. So the only particle that this could be would be the gamma. So all we're doing is making sure that the numbers on the left are equal to the numbers on the right. That is it. Nothing crazier than that. So go ahead and try these ones. Pause, take a second, and work them out on your own. Okay, so let's do this together now. So we have 196 up top, 196 up top. That means we need to have a 0 for our particle. 82 and 81, that means I need to have a -1 here. So let's look back and see what particle has a 0, -1. So that was beta negative decay, and that is our beta negative particle. So for the next one, we have a beta positive decay, and I only know that because there's a beta positive. And so now I'm going to finish this up. So 28 plus 0 still gives me 28. 15 plus 1 gives me 16. Now for this, I'm going to need my periodic table because I need to know what element has an atomic number of 16. So sulfur has an atomic number of 16. So the next one, we need to figure out what the particle is. So we have 226 and 222. So I'm going to need to have 222 plus 4 up top to get me to 226. And on bottom, I'm going to have a 2. So this is going to be alpha decay because that would be a helium particle. And I'm just basing this off of the chart from the last slide. Okay, the last one, we're going to have a 0 up top because 73 and 73, there's no change. And we're going to have a 0 on bottom. 30 and 30, there's no change. That would be our gamma. So this is all that you guys need to be able to do with that fancy chart that we had a couple of slides ago. Nothing crazier than this. And we're going to have some practice on this because I know it's a little bit tough. So at this point, I want you to look at your practice part, and I want you to go ahead and answer question number 2 and 3 on your practice. And then I want you to skip all the way down and do the decay practice on the bottom. Make sure that you can do that part before you move on. If you can't, go back, rewatch the last few minutes. All right, the last part of this section, or this section of notes, is going to be the average atomic mass. And remember, the average atomic mass is found on your periodic table. It's always going to be the decimal number. And this is the average mass of all the isotopes of an element. And we have to take into account something called the percent abundance. And that is really just saying that some isotopes are more common than others. So you would have to be given data like this, where I give you the isotope, the mass of that isotope, or you can just use this mass here if I don't give you this. Sometimes I won't give you that. It's not quite as accurate, but you can still do it. And then your percent abundance all the way on the right. So the way that you do this is we're essentially going to do a weighted average. This is the same way that you would calculate your grades. So the first thing you're going to do is turn the percents into decimals. Okay, and then you're going to multiply that by the mass. So here we go. We're going to do 0.9890 times 12.000. Don't forget to keep your sig figs. We don't want to lose those. And that is going to be the mass contribution from carbon 12. We're going to add that to the mass from carbon 13. So I'm going to scoot this over a little bit because I can't write smaller. So 0.0110 times 13.003. That's from carbon 13. And then we just plug that into our calculator and solve for our answer. So go ahead and make sure that you can do that. So at this point, after I've plugged it in, I'm going to come out to 12.01. Okay, so 12.01 is our average mass. And I want you to notice that this is very close to carbon 12. Okay, and the reason why that is look at that percent abundance. There are way more carbon 12 atoms than there are carbon 13. So the average atomic mass should be very, very close to the carbon 12. If you look at the average atomic masses, they should give you an idea of which isotope is most abundant. I almost forgot my units here. This is measured in atomic mass units. Don't forget your units on your numbers. So now that you've seen me do it, go ahead and try these 2 practice problems, and then the answers are on the next slide. So I want you to pause, practice these, give it a shot, plug it in. Don't forget your units at the end. So hopefully you've tried it. Here's the answers from the last slide. And at this point, I want you to take a second and go ahead and work through the last parts of your practice problems. So that is question numbers 4 all the way through 7. And that should be the end of the practice section, and all we have left is the summary part. So summaries are really, really important. You might think they're the part that you should skip over in the lesson, but they're really not. This is the part where you can take everything you learn and you put it in your own words. The more often you do this, every time we do notes, every time you do a reading, anything like that, it really helps solidify things in your brain. And if you can put them in your own words, then you understand them better. So make sure that you discuss what makes isotopes different from neutral atoms and how isotopes can be formed. Also, discuss how isotopes give rise to average atomic mass. It might also be helpful to talk about what causes radioactive decay and what is the purpose of radioactive decay. Why does it even happen? But try and put this in your own words and only focus on the key ideas. That's a small box that I gave you to write in for a reason.